consists, so the most, or the most common way of choosing these points xi is to consider some interval here. Say you have an interval here, AB, and then you choose equidistant point. ايش عين drawing?
Yes.
Okay. So with a step h, and you are going to find, okay, so basically if you have a function here, f of x, okay, you discretize the numerical methods. You always use, okay, discrete points, because in the computer, okay, use discrete numbers, so you cannot, okay, compute the integral with infinite number of points. So you need to use, okay, discrete points, and so these are the xi. Okay, so x0, start by x1 till xn. So basically, if you have n points, okay, you have n minus 1 interval. Yani the interval h, okay, or the step h will be b minus a over n minus 1. ليش؟ لأنه if we have n points, we have n minus 1 interval. Yani if I have here 3 points, okay, so I have 2 intervals. Okay, so the step h is b minus a, so the length of the interval a b divided by the number of points n minus 1. So this is called the step. Okay, now any point xi can be expressed as, if you there are equidistance by step a, as equal a plus, okay, I minus 1 multiply by h. ليش I minus 1؟ لأنه if you start from I equals 1 till n, okay, for I equals 1, then x1 is equal to a, and then x, okay, and xn is equal to b. If you define these things like this, then I equals 1, you get 1 minus 1 a, and for n I equals n, so you get n minus 1 and minus 1 plus b minus a, you get b. Okay, so this way you define n equidistant points on an interval a and b. So the most common way to compute an integral is to define n equidistant points and to express your integral as a sum of omega I f of xi, where these omega I are the weights. Okay, now we will see different methods, and for each of the different methods there will be, okay, the weights will be different. So the first method that we will see is the rectangle method. Make a new chair here. Okay, so basically here, okay, in the rectangle method, what you do is that, I'm just gonna correct the graph a little bit, because here I took n plus 1 points in my definition, but here, so it's coherent with my definition. So I'm gonna take here till n here, xn. Okay, and here it will go minus 1. Okay. Okay, so if we have here, the rectangle method consists of approximating the integral by a sum of rectangles. Okay, so basically, let this come in. The left corner approximation consists of using, okay, so if you have the point x1 till xn, the height of the rectangle will be f of x1, okay, of this first rectangle here. The height of this second rectangle will be f of x2, f of x3, f of x4, etc. Okay. Now, this is called the left corner approximation. So it consists of approximating the integral from a to b of f of x dx as a sum of h multiplied by f of xi, the sum from I equals 1 till n minus 1. ليش n minus 1؟ لأنه when you get here, for example, at x6 here, okay, then okay, that's it. You don't have another rectangle if you start by the left corner. Now, instead of starting by the left corner, you can start here by the right corner. Yani, for the first rectangle, the height of the first rectangle will be f of x2 instead of being f of x1 here, okay? So you can use f of x2 here. Okay, f of x3, etc. So it's the sum here. It will be go from I equals 2 till n, in this case, instead of I equals 1 till n, of h f of xi. Right? Now, as you see here, when the function here is increasing, okay, the left corner approximation, okay, will give you a result that is inferior to the real result. So it will underestimate here, okay, because it's increasing the function. Now, when it's decreasing, it will overestimate, okay. And here is the same thing. Here it will overestimate when it's increasing. When it's decreasing, it will underestimate the integral. Okay, so in order to have something in the between these two, you can use, in fact, the midpoint approximation. But the midpoint approximation, okay, you need to have additional values, which are the values of the midpoint here. Okay, the values of this midpoint here, and use it as the height of the rectangle. So sorry. So it's just 1, 2. So here it's still n minus 1 coming, the sum. Okay. All right. So the midpoint approximation, the height of the rectangle is the midpoint between xi and xi plus 1 here. So it will approximate the integral for a to b f of x dx as approximately h multiplied by f of xi plus h over 2 sum from I equals 1 till n minus 1.
دكتور ما لازم تكون لا n.
No, it's still n minus 1. طلع. You have n minus 1
اوكي
rectangle.
اوكي فهمت.
You have n minus 1. In all the cases, you will have n minus 1 rectangle, and you have n minus 1, in fact.
اوكي فهمت.
يعني لازم نظبطها بالرايت كورنر كمان. رايت كورنر
The right corner goes from 2 till n, so you have n minus 1. Okay, the right corner takes the left corner one, so it goes from 2 x2 till xn. This is right. Okay. Okay. And you could have gone from 2 till n if it's xi minus h over 2. It's the same thing. It will be the same expression.
صح.
It's the same thing. And you can go, whether you go from 1 till n minus 1 or whether you go from 2 till n, it's the same. Because here, this point here is x6 plus h over 2. The x7 here, okay, we don't use it here. Okay, so this is one, it's xn here. لأنه أنا بهيدا السلايد كنت عم بستعمل a little bit different notation. استعملت n plus 1 points. يعني this slide was correct بس إنه استعملت n plus 1 points and n interval. You can use n plus 1 point and n interval. Okay, or n points and n minus 1 interval. It's the same thing. Yeah. Okay, whether you have n plus 1 points, then you go to n here. Okay. Okay, but no, let's not complicate things. You have n points, then you have n minus 1 interval, and you will have n minus 1 rectangle. So this is the simplest method. It's the rectangle method. Implementing this numerically, it's not difficult. You just have, if you have a given function, you define the interval, okay, and then you just, in fact, make a for loop. Okay, you make a for loop and then you calculate this quantity. So if you have a given interval that is discrete, okay, you discrete some interval, you discretize the interval, and then you calculate the integral. The integral. Now, suppose that we don't want, to define this interval or the number of points in advance. Let's say we want to compute this integral up to a given precision, let's say 10 minus 6. So we want to increase the points, okay, at each time we want to increase the points. So the thing is that you cannot just increase 1 point, because if you increase 1 point, then you will change the step. So ما فينا نزيد point إذا عندي, let's say إنه I want that to calculate this integral with some given precision, right? So I want to calculate this integral with a given precision, okay? I can say, okay, I will increase the number of points till I get this precision, because the more you increase the number of points, the more your calculation will become accurate. But you cannot just increase the number of points, because when you increase the number of points, you must recalculate do all the recalculations, right? Like if you have 100 points, let's say, you calculate your integral. If you want use 1000 points, you recalculate all the integral, because the points differ, the steps differ between the points. So in this context, we can develop an iterative approach for the rectangle integration. So if we want, I said, if we want to calculate this integral till a given precision, yani we want to increase the number of points till we get the integral up to a given precision. Okay, so the idea consists of, okay, we start the first step, we have these 2 points A and B. Okay, so then we have one rectangle, so H is equal to B minus A. Okay, and the integral here, the approximation is I1 is equal H f of A. H f of A if it's the left corner.
Left.
Okay. So now in the second step, what I will do is that I will cut this interval in half. So I will increase the number of points. I will have 4 points of integration. So here I have, okay, cut the interval in half. So A plus B over 2 here. And then I have these 2 rectangles. So step 2, H is equal B minus A over 2. And at this step, okay, this integral is equal to B minus A over 2 by f of A plus f of A plus B over 2. Now, I will express, okay, this integral as the previous integral, yani I1 over 2. Okay, and I1 is B minus A by f of A, okay, the first integral, over 2, so it's I1 over 2, plus H f of A plus H. Why I'm doing this? Because, okay, I want to derive a general formula now for any step. And what I will do is that I will use the previous calculation at a given step. Okay, I will use the previous result of the previous calculation. So this, like this, I will we will save some computational time. Okay, so we don't recalculate all the points. So we double the number of points and we use the previous value that we already calculate. Now at the step 3 here, okay, so at the step 1, okay, I had, this is the number of intervals. So I had one interval here, n equals 2. The second step, n equals 2, I have 2 intervals. Step equals 3, n equals 4. Okay, so this big N here is the number of intervals. Okay, it's not the number of points. This is the number of interval. Right, so because I have then 4 intervals here. Okay, so H is equal B minus A over 4 here. So here I3 is equal to B minus A over 4, okay, multiplied by f of A plus f of A plus B over 4 plus f of A plus B over 2 plus, okay, f of A, 3f of A plus B over 4 is these 4 points here. Now if we express this integral, okay, in function of the previous integral I2 here, right? So I can re-express this as the following here. So I3 is equal to I2 over 2 plus k equals 1 till 2 H multiplied by f of k plus 2k minus 1 H. Look, this, so the I2 was B minus A over 2 f of A plus B over 2, and this one plus this one multiplied by B minus A over 4. Here I had B minus A over 2, and this is, these two here quantities are I2 over 2. All right, and then I'm left with the f of A plus B over 4 and f plus 3A plus B over 4. Okay, يعني I'm left
Okay.
with the odd terms here. يعني okay, so I can express this. Okay, k equals 1 till 2 f of a plus 2k minus 1 h. Okay. Plus 2k minus 1 h. Do it. So you have like k equals 1, you have 1. Okay, so you have f of a plus h, where h is now b minus b over 4. Okay, and for k equals 2, then you get 3h here, yani this thing, yani a plus 3h, where h is b minus a over 4. So this now becomes the general formula now for any step, at any step n. Okay, when I continue cutting the interval, like increasing the number of intervals by multiplying the number of interval, okay, by 2, yani dividing the step by 2. Okay, so okay, I get that at any step, at a step n, I have that the next step is the hn plus 1 is hn over 2. Yeah, I am at each step I'm making h is equal h over 2. Okay, so I start by this h, I divide by 2, I divide by 2, etc. Okay, now the number of intervals here, okay, if you the number of intervals is 2n minus 1, where n is the step, yani is a step n. Okay, so at step 3 it's the number of intervals is 4. Okay, so like this I derived a formula, and the numbers of step, the numbers of interval at a given step is 2n minus 1. And then the general formula for the integrals in plus 1 is equal in over 2, okay, plus hn plus 1, where hn plus 1 is equal hn over 2, multiplied by the sum from k equals 1 till n over 2 here. Okay, now شوفوا at n equals 4 I had 2. Okay, f of a plus 2k minus 1 hn plus 1. Yani the odd, this is the odd term. Okay, I have at a given step, I have these ones. Okay, this and this, and I don't have these quantities. I have this and this. This is the previous integral divided by 2. Okay, and these ones I don't have them, so I need to calculate the sum. So I don't recalculate all the sum at when I increase the number by 2. The simplest method is, okay, I increase the number by 2 and then I recalculate all the sum. But this is not very efficient from a computational purposes to recalculate all the sum. So this is an efficient method, okay, to do it. So you don't recalculate all the sum. You just recalculate the points that are added here when you divide the interval by 2. Okay. So these are the correspond to the odd term. Okay. So okay, so now if we want to write the algorithm, okay, so if we want to write the algorithm for this method, so first I start by defining the interval A, the interval B, the interval AB, and the points A and B. Okay, that's not my problem. The precision epsilon that I want on my integral, for example, 10 minus 6, or the function f. And then I start by doing h is equal b minus a. I is equal h f of a. So this is the first integral. Okay, the first approximation at step 1. Then h is equal h over 2. Okay, and I1 is equal h f of a plus b over 2. This is the second. This is the second step. Okay. So here, just 1 minute. So here it's h, so it's I over 2 plus so I1 نكبرها شوي. Okay, it doesn't matter. Okay, so h, so this is the first, okay, step. h I is equal h of a. So this is the left corner approximation with just the 2 points a and b. And then at the next step, okay, at the step 2, then I have, okay, h is equal h over 2. Okay, and then I make I1 is equal I over 2 plus h f of a plus b over 2. Okay, so this is the integral with the 3 points here, okay, or the 2 intervals. Okay, so the integral with the 3 points a, b, and a plus b over 2. Okay, and n equals 2. Why? Because you have 2 interval at this point. And now we will enter and make a while loop. While I minus I1 is inferior to epsilon. Okay, while I minus I1 is inferior to epsilon, I equals I1. I is the you assign to I, okay, the old integral, the integral at step n, because now you calculate at step n plus 1. Okay, you divide h by 2, so h becomes h over 2. Here r equals 0, r is for calculating the sum, okay, the sum on the odd term. So, and here k equals 1. Okay, so k equals 1 is like for the for loop. Now you make a for loop. Okay, so you will make a for loop till I have to modify a little bit this diagram. I will send you the diagram. Is because here you will, this k equals n over 2 must be here up. Okay, but in any case, now you will have a for loop. You make a for loop from k equals 1 till n over 2. Okay, from k equals 1 till n over 2, you calculate the sum r equals r plus f of a plus 2k minus 1 h. And when you finished, then you calculate I1 is equal I over 2 plus r. And what you are calculating is this. All right. What you're calculating is this sum here. All right. So that's what we are doing. Yani at each step, we are dividing h multiply by h over 2, but we are saving the old value, okay, and the new integral. So we stop while the integral at the step n plus 1 doesn't differ so much from the integral at step n. And I1 minus in plus 1 minus in is inferior to some precision epsilon. But here instead, I need just like to save just the two steps, at step n and at step n plus 1. Okay, I don't need to save all the different step and put them into a vector. Just like need to save these two different steps. So I make the for loop, and then I make I1 equals I over 2 plus R, and then I increase n by 2, so n becomes n equals 2n. Okay, and then I repeat the process, and then I repeat this till I minus I1 is inferior to epsilon. Right, and then when I minus y1 is inferior to epsilon, I print the solution. Now just like modify this, because I mean this is true, but this is better that this condition is up here before this R plus. Okay, it's more it's better. This is just a for loop. You make a for loop R, okay, 4k equals 1 till n over 2, and you make this sum. All right, any question?
No.
Nobody else has a question? Something is not clear?
كله منيح.
So now we are going to discuss the trapezoidal method. Okay. So the trapezoidal methods consist of approximating here the integral by, instead of rectangle, okay, a sum of trapezoids. Okay, so so now, instead of taking the sum of rectangles, you take this the sum of trapezoids. All right. So basically, what is the area of, let's share a new screen here.
دكتور بعد فيها من دقيقة وعنا صفحة 3.
All right, so I will stop here, and we will continue next time. Okay?